All right, great. So we scaled our site. We trimmed out some pieces. We just scaled our object to 1 inch equals 125 feet. Let's double check the distance, how big this is. So yep, it should be 4 inches by 4 inches. So it should fit most of everyone. It should fit everyone's build plate. We just offsetted our initial site. 1 inch equals 1/64th of an inch. And now we're going to extrude that new tolerance curve. We're going to extrude it down to the midpoint of our thickness of our print. So we also want to cut this hole, so we're going to highlight this. Actually, we can delete this curve now, and we don't need it. We're going to split. We're going to split using this curve as a cutting object. And now we can delete that. Actually, we won't delete it. We're going to move this thing down. And we want the end point of that. Great. We need to put a bottom to this. And we also need a side to this. So we're going to take our surface from 3 to 4 points, and we're going to hover over this endpoint. We're going to take this endpoint, take that endpoint, click on that endpoint. There we go. We got our surface right there. We also have this. So we're going to do the same thing. We're going to hover over it. We're going to grab an endpoint, an endpoint, endpoint. And sometimes you get this. Sometimes it'll say perp, which means perpendicular or end. Sometimes it's good just to turn off your perpendicular and just keep your endpoints on. Sometimes you'll just snap to the wrong thing, and there's a solution to fix that, and we'll go over that. That's like the next thing, because we're going to perform analysis on this. So we got our site, we got this, we got that. So all these are all made up of little individual pieces. So what we're going to do is we're going to highlight our top surface. We're going to hold Shift. We're going to highlight our extrusions. We're going to highlight that bottom. We're going to highlight these sides, and we're going to highlight that bottom as well. We're going to type in join. And that should join all these together. And a good way to do this is if we go under display and we go into our ghosted viewport, we can start to understand how some of these faces are interacting. So we notice that when we have this selected, there's a bottom face to this. This is separate. There's faces that are colliding here. There's that. So we want to get rid of all this. So this whole thing is just one hollowed shell. It just makes so once we have it one hollowed shell, it just makes our 3D printing a lot faster and a lot easier, and it doesn't confuse the printer. As soon as we get into something that's not a hollow shell, like if we had a box, for example, and we're going to get rid of this face, and we're going to so if we have a geometry like this is a huge issue for 3D printing, because this object is not considered watertight, because now this becomes the computer's reading this as, oh, that means I got to 3D print this hollow, and I have to understand the thickness of this. Well, this is a plane in 3D, and planes have no thickness. So the 3D printing will error out saying, okay, I can't 3D print this because there's no thickness. I don't know how thick I can make this. As soon as we make something watertight, like an object like this, like a closed box, it understands that, okay, I can 3D print this because I don't have to worry about the inside. I can do all my calculations. I can fill in the necessary structure to fill this in. And that's 3D. And so that's why it's really important to, when we 3D model stuff, it will know, it's important to keep that hollowed because it will know, okay, what I can 3D print. When I have two faces that are colliding, it could add extra time, unnecessary extra time for the 3D print, because it may read this as, oh, this is a wall. I need to 3D print this wall, and I'll go through all this extra effort to adding faces or extra number of shells on this where it didn't need to. It was unnecessary, and you wasted plastic and you wasted time. So it's important just to model cleanly and model hollowed shells. So let's get rid of some of these faces. So the first class I mentioned, Boolean union. That's going to select surfaces. It's going to select some surfaces or polysurfaces. We're going to select this. We're going to select that. We're going to click enter. And we notice when it did that, it got rid of some of those faces. Those faces on the inside, it just got rid of them because now it unioned all this as one object. We're going to do the same with this site and this building. We're going to Boolean union. We're going to select the site, this. We're going to enter, and there it is. It hollowed out that bottom, and it made this into a hollowed shell. Now, sometimes your Boolean unions won't work. For example, if I take a few steps back, I can't Boolean union. Say it may pick up a few things, but I accidentally dragged this, and now it's saying, oh, wait, well, looks like there's some double faces there, but it will say, hey, I can't Boolean union some things. The trick is just to, I've had better luck just Boolean individual pieces together. If you're still getting errors, it's because you have faces that do this. It may be really tiny bit off, but it's just enough for the program to be like, hey, this isn't closed yet. I got this little sliver here. And that won't work. The Boolean union won't work. And also it's not watertight. So how do you solve that stuff? There's a tool in Rhino that can help you. And it's called Show Edges. And when you type in Show Edges, it's going to ask you for surfaces. Select surfaces, polysurfaces, meshes, and you can select any number of them. And once you select it, press enter. And it's going to say we can list all edges. So that defines all the edges of these objects, or naked edges. Naked edges are what we're looking for. Naked edges are when something isn't watertight or isn't complete. And once you know, we have some naked edges right here. So, and there we go. When we click it, see it's not joined. We have this separate piece here. So what we can do is we either modify this geometry, like if we want to just move this geometry to close that face off, we can just click our move, highlight the end, highlight this and join it, and there it is. It's gone now. Because now it's a watertight object. If you're still having issues, you can start to change some of the geometry. You can start cutting it, like let's say if I accidentally move this out too much, the building's supposed to end there. You know, I could always start to do split. Split this object, and even that would fail. So we'd have to start manipulating this geometry here. And sometimes you might just have to explode this whole thing over again. And you just have to start piece things together. Notice that, okay, we can cut that. What about this face? Let's split that. Get rid of that face now. And then we can slowly start to build this thing up. Split this. Let's highlight all this and join it again and get our show edges. Oh, and we naked edges. We have a piece right here that we're missing. Let's double check. Yeah, there's a hole right there. Okay, great. Well, we got to fix that hole. We can't 3D print that. So let's get our mesh, our little 3-point. Let's do end to end to end to end. Join everything again. Let's show edges. Okay. All right, great. This thing is watertight and it's good for 3D printing. Sometimes.
I have a question real quick.
Yeah, what's up?
So when I do show edges, I don't get that little dialog box to pop up. Is there another command to pop that edge analysis box up?
If it doesn't pop up, it may be, do you have 2 screens?
Yeah, more than one.
Okay, it might be floating. Sometimes Rhino likes to throw one of those menus on a different screen and behind some commands, menus and stuff. If that's not the case, you have to select your object first, then click enter, and it should pop up. It won't, if you type in show edges and enter, nothing's gonna pop up because it's like, well, I failed to find stuff. I have to select objects and then click enter.
Okay, thank you.
Yep. So, sorry, we got our piece that's watertight. We don't need this guy anymore. There's also, well, let's say we have, let's pretend we thought everything was great except we're missing this. And the next step is is we're going to mesh this. Right now, this is a B-rep. And the way we 3D print things and even the way we manufacture things is through meshes. So meshes, I think I mentioned this on the first classes, meshes are defined through points. It's pretty much, you have a surface that's made up of a series of squares or rectangles. Right now, this is just a surface that's defined by boundaries. So 3D printing will only read meshes. The file type that all our 3D printing software runs on is an STL file, which is a file that reads meshes or converts things to meshes. Sometimes when it's things like this that are relatively simple, you can just export this as an STL, and the software is smart enough to understand that, okay, this is a mesh. I'm going to convert this into a mesh, and it's pretty clean. Sometimes when you're dealing with objects that are very complicated, when you mesh something, the software may have some things that screw up. You may notice on some of your towers, and you may notice it on this tower, is that it's kind of, it's segmented. It's not the cleanest way. It's not the cleanest thing you've seen. It's not the cleanest. You might see some of the light, how it bounces off. You might see some like triangles on it. That's how the program reads them. This was a really smooth surface in Rhino, but as soon as you mesh it, it triangulates this and it segments it. And depending on the quality of the print, especially here, the quality of the print, how smooth you want this, determines on how you wanted to mesh it. You can just do the simple default mesh. That's fine. And for this assignment, I'm not going to mark you down. I'm not looking for. I'm really just looking for make sure you guys can 3D print this. But if this is a really professional 3D printed model, I want this to be the highest quality. This mesh count is really important. I want this to read as smooth as possible and not see this triangulation. So I would add a lot more. I would actually mesh it in Rhino, and I would add more mesh surfaces. There are options when you export it, but again, you don't have that much control over it. With this stuff, we're doing some really simple forms. And like I said, if you do have a complex form, I'm not going to grade you against it or anything. This is stuff further down the road, but just something to keep in mind when we do that. Can you guys see my screen?
Yes.
Okay, cool. So we know we have a hole here that's but we're gonna mesh this in. So we just type in mesh, and we have our controls. How fewer, more polygons. Since this is pretty simple, it doesn't quite matter. We can always say we just stick it right in the middle. We always preview it also if we need to, if it's really important. Actually, if you have a model like this one, this was really important on how we wanted to mesh this. This took a lot. This has a lot of intricate pieces to it, so meshing was really important on how we wanted to do that. So we meshed this all in Rhino and made sure. And I mean, the file was pretty massive just to make sure that we had all the smooth meshes that we wanted to. But with this, our other stuff, it's not that bad. So we'll just click mesh, okay. And the tricky thing is it's going to create a duplicate model of your object right on top of it. So when you hover over it, it's going to say poly surface mesh. We want the mesh, so we're just going to select the poly surface. We're going to type in hide. And it's just going to go. It's just temporarily going to go away. So let's do show edges again. All right, and once you know, it detects naked edges. So we're going to. We need to fix this. Let's say we did everything, we meshed it, and we found a hole. Well, there's ways that we can fix it when it's a mesh too. There's actually a pretty simple one called fill holes. Oh, close mesh. Close mesh. Is it fill all holes? Yeah, fill mesh holes. And it's going to ask us. Whoops. It's going to ask us some of our boundaries, and it can fill up some of these holes. There's also a whole bunch of great tools under the mesh dropdown. There's actually a mesh repair tool, which says fill all holes as well, instead of typing it in, and it will calculate it. Sometimes it's not the best, like this one. It has added this little, looks like wasn't perfectly straight. There's also some mesh booleans, mesh different, same, very similar tools. Sometimes we may have some surfaces that are just barely touching each other. We can always weld them together. We can select, these lines are called vertices, so we can always select these vertices and weld them together so it becomes one and it keeps it clean. There's, like I said, there's trim. We can, if things are too crazy, we can always reduce the number of meshes. And we can start, so right now this is made up of 496 polygons. And we could always reduce it by a certain percentage if it's just too much. If it's too complicated of a form, we can reduce it. It becomes a little easier to deal with. Now it does affect the shape of it. It does affect the form of it. So we got to be careful. If we have a sphere and we reduce it, the sphere is going to get segmented and it's going to start to look like a rock a little bit. So we have to be careful and conscious of how those settings work with us. But for this one, we can just say mesh repair tool. Let's say fill holes. There it is. And then we can always show edges. And once you know, it's all watertight. And we do this, and the nice thing is with Grasshopper, we know right off the bat if the object is the object is watertight or not. It will say that in our panel. All right, so we'll just draw a rectangle. We're also going to, it's just going to move this. Move this to 0, 0, 0. We're going to draw a rectangle. We'll do 1 inch by 1 inch. All right, great. There's a big rectangle. Oh, because also be careful. Sometimes when we scale things, since our original document was in feet and now we're worried about inches, we could always go into our units, convert this into inches. Do you want to scale it? No. That should be fine. Oh, my bad. Where's my object? There it is. And we'll switch units. We'll switch to inches, and you do want to scale it. There we go. Now this should be still 4 inches. Yes, okay. Good. But with our, so in Grasshopper, we'll have our rectangle, we'll have our move, grab a quick series. Oops. Let's do it quick. So right now, when we loft this, and we're just going to put this to the side. Right now, it is it's an open surface because we're missing that top and bottom, so it won't 3D print because there's no thickness to that. And we can either, when you say panel, and say open BREP. So it's an open geometry, it's not watertight. That's not good. We can't 3D print that. So let's cap it off. We should know cap by now. So we'll cap that off. And then we're gonna take that, we're gonna plug that right back into panel. And now it says closed BREP. Now that is watertight. So let's just bake that right in. For this, we'll just say default. And let's just unpreview this. And there's our little tower. Now with we should have our site as well with this. That's one thing, our actual property line. So we'll have our property that fits right into this that we actually didn't 3D model that we'll later insert. But for this sake, we're just going to I'll just remake it really quick. Vertex. Remember, we did an offset to that. So we're just going to offset this. 64ths. We'll put that in. Great. Curve down. We're going to make sure that we hit that vertex. Cap it. And this should already be right on your planted on your site when you bake this thing. So that you should be able to move your tower right onto your site because you have all your setbacks and stuff. It's just a quick example. It's just me going pretty quick, but all that should just be included onto your stuff. So you wouldn't have to do this. But we have something like that. And for now, let's just hide this, for example. Get rid of that for a bit. So we got our object there. Well, let's, and they're both watertight. Let's just do a Boolean union. We'll select this, select that, and there it is. Let's switch to our ghost. And see, it got rid of that. So we have our tower. Let's bring back our site. Let's select it. We'll mesh that. For this one, since we want it, we'll go more polygons. And you're going to notice that it will be very, very subtle, but the 3D printer is so accurate, it will pick up those subtleties. But when we loft it, we're going to hide our mesh. It's made up of, some of the programming just did straight sections of it. Some other ones will triangulate it. But we got our little site, we got a little tower. We can delete that curve, we don't need it. But now these both are ready for 3D printing. If this thing is too tall, which you can later export it, we can start to understand that. So like what to do. And what we do is the exact same detail as this. You know, we're gonna chop that in half and we're gonna get a nice flat surface when we do that, and we can start offsetting, offset these in and create a little indent and groove that these two pieces will fit in, just like in the assignment. And it's same thing. We'll just snap. We'll make it watertight, and it would be good to go. So in this one, this is pretty good. We just want to make sure we got rid of all our stray lines. So we'll do a selection filter. We'll uncheck all our stuff. Make sure that curves are the only thing that are selected. We'll highlight everything. Okay, great. There's no curves. We'll have our show edges on, show edges. Okay, there's no, we're good. We don't have any naked edges. We can close that down. So this is ready to export. So we're gonna highlight, we're gonna say, we can actually highlight both if we want to when you say export. And when we export it, we want it to be as an STL. There it is, stereolithograph. And we're just gonna label it as, oh, you know what? So some 3D printers, before we export it, some 3D printers they have built-in unit converters. Right now we're in inches. We went from feet to inches. 3D printing reads millimeters. All the data that it tells the software to read is in millimeters. So we need to convert this into millimeters. So there's some that most you can import the object into the 3D software, 3D printing software. If it's in inches, it's either really big or really small. And there's just a button that says, hey, convert inches to millimeters, and it'll scale it correctly. Others don't. So it's good practice in Rhino. Just go back to our units command. We're just going to switch it to millimeters. Yes, we're going to scale it. Yep, that's fine. It's on my CAM software. We're also going to move this to the center point. Just as good practice. A lot of times the software knows, like, okay, we're going to move this to the build plate. Sometimes it may be way off in the distance. It's just good to keep things on a 0, 0. So now we're going to export. We're just going to highlight everything. We'll type in export. And we'll go down to STL. Go to options. Binary is just, we can just click it on binary. That's that's standard. We'll just say, don't worry about the other one. All right, and so there it is. It saved successfully. So in this example, we're going the slicer software. The slicer software is the software that usually comes with your 3D printer, or it's the software that that you could download separately that could be compatible. Not all software is compatible with certain 3D printers. My 3D printer is very old. And it's funny when I say very old because it's only 4 years old, but in 3D printing, it's pretty old, and it's actually, I can't even use some of the newest software. But Cura, for this example, I'm just going to talk about Cura just because it has some, just graphically, it works. I can talk a lot about how the 3D printing is going to do its thinking. It's also a great software. It's probably one of the best I've used. So most of this will be on that. Yours may be different, but it's going to be very similar. It's not like going to be completely different. It's going to follow these basic principles. You just may not have some options. Like my 3D printer has very limited, my software has very limited options. I really have only a few customizations, but the new stuff, it's very flexible. So we're going to launch Cura. We're going to open file. We're going to go into where I saved that. Oops. Oh, there it is. It snaps right there. And here's our building. So if you have a single extruder, you're all set. You're stuck with that one extruder. If you have two extruders, options up here tell you what extruder you want to use. Now, the two popular, PLA is probably the most popular plastic. It's a natural-based plastic, so it's less harmful for you. Now, the 3D printing companies will say it's not harmful at all, but you are burning plastic and extruding it, so it may be probably good to have some kind of ventilation. Not a lot. I have mine in my basement, and I sit next to it all the time while it's printing, so it's fine. It's usually ABS, that is a chemical base that does stink. It smells like burning plastic when it prints, and they do recommend there's some ventilation for it. ABS was pretty popular back when it first started. It was like 50-50 ABS and PLA. It's predominantly PLA. I have a hard time finding ABS, and ABS is also a pain to print because it requires much hotter temperatures. Some of your 3D printers may have a heated base plate, and for you just to print ABS, you have to have a heated build plate. Like I said, some 3D printers don't have a heated build plate, so you can't print ABS. Honestly, that's fine because PLA, you can do so much more with PLA. There's very little advantages of ABS. But so PLA is predominantly what we're going to print with. There's also a PL. It's escaping me right now. It's a water soluble plastic. So that plastic is pretty sensitive to moisture, and it's great for 3D printing our structures and our rafts. And I'll get into that in a little bit. But right now we have our basic thing. This doesn't need any special structure to hold up this. This is all pretty straightforward. Everything is just pretty vertical that we don't need to worry about too much. So we're going to click on our print settings. This is our profiles. This is how thick it is per layer, and this is these are incredibly small layers that we're talking about. These are microns. So, and I don't even know if my camera resolution is even that good that you can see some of the layers to this. But this is at 0.2. This is actually a low setting. So it can get you can get something that is incredibly fine where it's very difficult to see some of the layers that 3D print this. Even with this one, this is actually at a really low setting. In fact, if you the photograph that I took of this, you can see the layers pretty clearly, but it just shows like when it says 2, which is considered a low setting, it's still pretty good on what we can do. And we can go all the way down to, for Cura, you can go all the way down to 0.1 to 0.06. These are all based on your 3D printer hardware. My 3D printer can probably only go up to a 0.1. The 3D printer that we have at my office is an Ultimaker, which can go down to a 0.06, and it is almost non-existent. The line is. It is so small. So it's all based on your hardware, what you have. We also have, the next thing is our infill. So our infill is the amount of structure it's going to print inside this 3D print. So we can, and predominantly it's pretty, on average, it's going to be a pretty simple grid inside. And I'll show you just a little bit what this grid looks like. Oops. Oops, hold on. I have to slice it. I do have to slice it. But what the software is it's calculating the infill, but we can see this does a pretty good job actually visualizing some of the layers that it's going to be making. And what is that command? Oh, here it is. So that is the actual grid it's going to be printing inside to help hold this up. So each one of these layers, so right now this is about 2,300 layers, and each one is it's going to be custom, and this slicing software is going to it's just like how Rhino is. It's based off our Cartesian grid, the X, Y, and Z. That's exactly how this software is going to run. It's slicing this model over 2,300 times, and for each slice, it's going to tell tell the processor coordinates that this extruder has to move. So it's going to say, okay, extruder move to 0, 3, 4. And I'll move to 5, 6, 7. And it's going to make all these coordinates. That's how it's going to know. So all those zeros and ones, every time it makes a trigger, it's going to send that to the motors. And the motors are going to work together. And it's going to move that extruder around and 3D print this. It's also important that when we level our build plate, that we have a little, just a sliver underneath the extruder and the actual build plate, because it needs a little bit of pressure, a little bit of squish for that melted plastic to start, and just a little bit. You don't want too much because then it starts to smear the plastic. You don't want too little because then you don't have enough force to help it lay down. So all these print settings should be under your instructions for your 3D printer. The test for me to make sure that the build plate is leveled correctly is if you stick a business card between the extruder and the build plate, and you get a little bit of a tug, not a lot, but just a little bit of resistance, you're all set. And that's pretty much the science to it. There are ones that are self-leveling that are smart enough to do that. For our desktop ones, they're usually not that sophisticated. But with Cura, we're able to kind of understand, like, okay, what these are going to be, and we also go back and change how the percentage of infill. Since this is pretty simple, the infill, like 20% is a lot. You probably don't need that for something like this. You probably can get away with 10%. 10% is a fine amount. Since it's so simple, you don't need to go any more complex. Let's go into with Cura. Cura's pretty simple, where they have recommended settings, and you can just say, I want a normal setting or a fast setting. These are presets. So as soon as you say, I want this fast setting, it will update all these variables for you, because it knows, okay, the company has tested these and it works for them. However, if you have a 3D printer like mine is not like that at all. I have to go through, mine's more of a trial and error. Your 3D printers may have a manual that come with it and just say, these are our recommended settings. And when I mean by settings, I mean by this. Your object infill, like with this, as I mentioned before, 10% works. The layer height, it's not millimeters, it's microns. It's 0.2. It's well, actually, yeah, maybe it is. But there's a number of shells. You know, how many times it's going to make a pass around the perimeter. So if we say shell, it says for this, it says wall. For Kira, it'll say wall line count 3. That means it's going to make 3 passes around the perimeter of our building, of the perimeter of this. Since this is all pretty basic stuff, it's if I used one and one seemed to be fine. And all that depends on what kind of 3D print you're making. What's the geometry that you're making? If you're making something that's very very thick, or I guess if it's if it's something that has a lot of detail on the outside, you probably don't want that number of shells to be high. You want that to be pretty small because sometimes it gets a little thicker on it. So, so it all depends on what you really want it to do and what the different operations are that you're trying to have. Your feed rate. This is the amount, this is the rate that the plastic is fed through the extruder. And for my draft settings, it was a 40 millimeters per second. You know, travel feed rate. Feed rate is the actual, like, how it moves the extruder. And usually these numbers are pretty close with each other. And then the print temperature. The print temperature is usually around 200, and it's not 250 degrees Fahrenheit, it's 215 Celsius. It's definitely Celsius. So that is usually based off your material. If you're using PLA, 215 is fine. With ABS, you might have to go a little hotter. It should say that on the plastic that you bought, or you can just look it up online and they'll have a series of recommendations. And then your heated build plate. If you have one, you can set yours between 80 to 90 Celsius, 80 to 90 degrees Celsius. If you don't have one, well, you don't have to worry about it. You just have to print with PLA and you'll be fine. But also, once you slice all your stuff, it also gives you an estimated time. So for this, if we sent this to this printer, it says it was going to take 6 hours and 15 minutes. And sometimes they'll even tell you how much plastic it's going to take. Mine's not that fancy. That number is purely based off your timeline. If we have a lot of time for a project, and this is a presentation model, I'm going to make this thing nice looking, and we got the time to spare, and we got a client who wants something that's really special, and maybe it's not. Maybe it's just for a really important presentation. We're going to put it to fine to extra fine. So if we just did fine, we're going to slice this thing, and we're going to have much more layers, and it's going to take a lot more time to do. So now we're looking at 21 hours just from switching from a 0.2 to a 0.1. And so with Kira, it calculates the travel speed because you want since it's slow, since it's a higher quality, you want your feed rates to be slower. You want the movement of the head slower because it's going to jerk around, and when it jerks around, it sometimes creates little inaccuracies. And if you look at mine, you'll actually see quite a bit of stray lines. That it's just, it didn't print exactly correctly. Yeah, like you get some fuzz along here. You know, it's because it was moving a little too fast. It's still draft, you know, but it's fine. You know, you really just you get some sandpaper, you chip it off with your fingernails, and it comes right off. Um, but it's just post-production stuff that you gotta do. Sometimes when you do a draft or low quality, you gotta chip away a few things with your fingernail or get a little X-Acto knife and start chopping things up. And it makes all these little small plastic fibers everywhere. Um, so just these are all the variables you have to come think about when you're 3D printing, because again, it takes a long time. So with this assignment, I'm saying it's like if you got to do a draft or low, just do it. All right, I want you to try to get these done. These aren't like highly polished presentation ones. It's more of just the exercise of rapid prototyping, cranking out as many of these as you can. And in this case, I'm just looking for 2 of them in your site and a test one. But if you see like a live design where they're just, hey, we have 6 ideas, let's just 3D print 6 of them, see how it goes. They're going to print them on the lowest setting, and they want these things cranking out as fast as they can because they want these to be printed as fast as you get so you can look at it, get the feedback that you need to learn from it, and update that 3D model and send it back to the 3D printer. That was the same process we did for the putt-putt one, was we put these at the lowest quality we could, and we sent it to the printer just to test them out. To make sure certain things fit. Sometimes we'll print at a low quality, but we'll crank the infill up because people are going to be stepping on these. We wanted to make sure that these are durable enough, you know, and if we're using the correct plastic to do that. So it's all about that. When you have a single extruder, it's really simple. You'll print all this as one. If you have a dual extruder, you'll print it all as one in this scenario because you won't need a second plastic. Well, let's say we're going to do this. We're going to do I'm going to delete that. We're going to do a show. And let's say we're going to do something cool. Like we're going to make this here. We're going to do box. We want some little focal point here. What if we had like this little, say, Tony Stark helicopter pad or something up here? If our 3D printer is going to go around and around and sees these as all these little loops, and it's just going to build up from here, how is it going to 3D print this? Because now, when it wants to come over here and start to 3D print this coordinate, there's nothing here to support it. It's just going to 3D print into air, and there's no pad for it there's no support for it. So the 3D printer software is smart enough to detect that. So we're going to re-export this again. Get rid of that curve. With this being so simple, I'm just going to have the software mesh it for me. We're going to delete this. File, open. And there it is. All right, great. So we'll do this at a quick draft setting and support. Actually, before we do that, we notice when we input Kira, and now all software will do this, we notice it's red. Red means it's unsupported. It means it's saying, okay, I cannot print this face without additional support. So we're going to click on the support. And what's that do? That's going to generate structure to help support cantilevered parts. And when it's a single extruder, it's going to use that same extruder. If you're using black PLA, all your support's going to be black PLA, and your finished model will be black PLA, and you're going to have to chip away and break apart this structure. The software is smart enough, though, to add a little buffer of plastic along your support structure and your model, so it will break off cleaner. It's not going to break off perfectly clean. There is still going to be some post-production. It's just like a little sanding or a little X-Acto knife action, but it will break off pretty easily. With a dual extruder, this is the biggest benefit of having a dual extruder. I can assign my second extruder as a different material, and that's where I want to use that water-soluble plastic, because I can have a water-soluble plastic print all my structure, and then I can just dunk it in water and let it sit for a few hours, and I can pull it out, and I'll have a nice, clean, finished model. And that's how we were able to get, that's how we were able to print this guy, because this whole thing was structure. This whole thing, it built entirely, actually, if you look at this the printable material, it's very little, because it's like this lattice structure. It's probably used about 4 times the amount of water-soluble plastic to print this, because it was all just these lattices and everything was a cantilever, and it just encased this thing. And then we just let it dunk for a few days. Now this took about 7 days to 3D print, but it was all that water-soluble plastic. And the more dense that plastic is, the more it's going to take. And it's actually like really, when it starts to dissolve, it's like really sticky and gunky. So you want to sit, the longer it sits in there, the more it just falls right off. Like we usually have it's weird because it works, the water-soluble plastic works really well when the water is a little bit warm and there's a slight current. So we use actually this cooking tool, like how you poach your eggs. So we put that in our little dunk kit tank, and it heats up the water to like 90 degrees, and it just has a little current, and so it really dissolves the plastic faster. But it's a great tool to have. The plastic is pretty expensive. Like most rolls, like I have a place called Micro Center around where I live, which they make their own plastic. So their plastic's like really cheap. It's like $15, which is like almost cheaper than Amazon's. But the water-soluble plastic goes for about $50 a roll, and it's very sensitive, because if you have like a high humidity room, that plastic's gonna start to gunk up on you, and you'll actually hear it pop, because it's starting to partially dissolve while you 3D print. So it's very sensitive stuff. There's a lot of like, okay, you got to check your humidity, you got to check all that stuff, because if you set it out, it's going to start to stick out. Or if it's too dry, it becomes really brittle and it'll break in the middle of your 3D print. We had that happen before, and you just, luckily our printer's smart enough to stop and detect it, but sometimes you may just have to start all over. But okay, so we have this, we have some ideas how we want this to go, and let's slice this thing up. And you're going to notice now, it took maybe 6 hours. It's going to take a lot more, because now it has to print all this structure. If we go into preview, and see, that's all the extra structure it has to print.
Can you share your screen?
Oh, yeah. Great. So now this is that's all the structure that we have to do. And if we start to slice that down, we can see it has a different pattern, and you can also see how it creates that little buffer there, so it's easier to break off from our main model. Also, we have you may notice that you have this little brim or a little outline that goes around our models. That's called a raft. Now, a raft it lays down an extra layer of plastic, just so it increases the surface area of your models, so it sticks to your 3D printer better. Because sometimes you may have that in the middle of the print, the 3D print may start to peel up a little bit. Well, when that does that, it kind of throws off all your other layers, because it makes that telescoping effect, because you have so many layers on top of it. So it affects the quality of your model. So this raft adds that extra surface area, and it helps glue that down better. And if you have Cura, there you have different levels of rafts that you can apply. My software, I only have one setting of raft, and honestly, I always have to use it on mine. There's some people that I know that hardly use rafts, but for mine, rafts is the best way to do it. There's also, to keep things on your build plate, you usually want an extra level of adhesion. And what I mean by that is use like a glue stick. Take a glue stick, and you can glue stick just literally, if like mine's a glass build plate that sits onto a heated build plate. So I sometimes will take a glue stick, and I'll just smear the glue stick all over the glass, and so you're actually gluing that print onto the glass. And so that's just another level of adhesion to it. And it's like the glue sticks that you use that are yellow that you use in kindergarten. Like they're like the super cheap stuff, and it works. And I usually have like a little paint scraper to help peel up the plastic or my model. Also, you could use Aquanet, that hairspray that I've used that a couple times. It's just they give you so much of it, and I've had it for a few years now, and I've yet to run out of it. I mean, and it stinks really bad, but that also works well. But I recommend doing that because even with this Ultimaker, like it's funny, Ultimaker is a $5,000 3D printer, and we were really excited opening it up, and what we found in the box was a glue stick that I used when I was in preschool. And it was like, this is what you use to hold down your model for extra adhesion. So it's pretty low tech, but it works really well, and I recommend just laying down some glue when you 3D print stuff. but yeah, it's just helps keep things tied down. What else? But yeah, when you have these cantilevers, it will start to detect when the software is smart enough to start to detect when to build this raft, this structure. And you can, depending on how advanced some of the software is, you can change the logic of how it picks up that structure. For this one, Kira, you can change the different patternings, and that's always pretty cool and sometimes useful. And another thing when we talk about infill is gradual infill. This is the only software that I've seen utilizes gradual infill. I'm not sure if any MakerBots or any other software or Slicer uses it, but gradual infill is really helpful, as we see this infill is constant throughout the model, right? Once it starts, it just stacks right on top of each other. Well, gradual infill, it starts very loose, and we notice when we click on gradual infill, we gray out our infill because it's going to gradually build up that infill. And the intent of it is to add the plastic where it needs to, and like when it has very detailed areas, it provides the extra level of structure, and when it doesn't need it, it goes away. And the software is smart enough to be like, okay, I'm just going to gradually go away when I need to, and I'm going to gradually reappear when I need to. And so this is it. So it will detect, okay, I need a lot of infill here to keep this up. But on this tower, since it's just the form itself has a lot of rigidity to it, I don't need too much structure. And so it will 3D print this hollow. It's trying to be efficient in it and the amount of plastic it's using. It sometimes adds a lot of time to it. Sometimes it saves time. It all depends on the type of geometry you're generating. I've had it where it was a huge time saver, and I've also had it where it's like this thing added a lot of unnecessary time to it. So it all depends on the type of form that you're trying to create in 3D print. And in this case, I actually added more time to it. So it's like, well, you have to weigh all that stuff. Do I want quality, or am I just trying to crank out this model? So that is all based on timeline and resources that we have. And then when we're done with this, you saved a file, or you export it, or what this does is this is a G code. So this G code is the code that actually tells the processors where to move the heads. So, and Ultimaker has their own special file type called the Ultimake format package. Frankly, the ones that I do is just a text file, and you can look at it and you can read all the coordinates of the text file. In fact, if you want to manually change it, you can. But in Ultimaker's case, they have their own special one. And when you save it, it creates it creates the Ultimaker file, and you plug that file right into the 3D printer, and the 3D printer understands, okay, what the processes I need to do. So if with mine was just a simple text file, I just tell it to read this text file, and it will understand, okay, I need to do I'm going to start heating up now. I'm going to move my extruder over here, and then I'm a program to build a raft. And okay, now I'm going to start interpreting that data, how to 3D print this, and it'll start moving up and 3D printing the object. So yeah, it is, and each one will vary. The process is exactly the same throughout all our 3D printers. There's a slicer program, and then it will generate a small file that the hardware will understand. That is given through all our 3D printers. It's really just the interface that's different for all our stuff. And that's kind of the challenge with the online class and everyone having different 3D printers, is that everyone is, if it's it's going to have a slightly different experience, or not different experience, but different interface with the software. So that's where you guys might have to just be a little more might have to read the manuals and stuff. That there's things that I may not be familiar with. Actually, some of the printers that you guys purchased, I've never heard before. It was great that you guys are and I thought it was, first of all, fantastic. It could be a fantastic printer and a great deal. But again, I have no experience with that. I usually have some with Ultimaker and my Chinese ripoff of a MakerBot, which is a unique firm or unique company. But yeah, so that's where a lot of my experience on different software on that is maybe different. But the nice thing is all these are very similar. So these numbers here, you'll have some of these exact same parameters for yours. They may be called different. Like I noticed that the Cura called the shell wall line count, but it's still under the shell command or shell category. So it's just, they may have small nuances that are different, but essentially the core idea is exactly the same. So does anyone have any questions? We're kind of wrapping up, getting close to the end, or we are at the end.
Any particular color? We can pick any color.
Pick any color.
Okay.
I actually would kind of regret it. I did black, and I was like, well, black is the one thing that it doesn't pick up shadows, but you can do black, you can do green, pink, whatever color that you need, that you have. Yeah, and yeah, and when you photograph it, just photograph, you just take it with your cell phone. Just try keep it a little nicer. Don't send me a very blurry picture, but at least try to keep it a little nice so I can read it and understand some of your process. But yeah. Any other questions? Well, cool. It's funny. It's like, this is going to be a quick class. I'm going to talk about assignment 4. We'll be all set and out. And gosh, now it's like we're overtime. But if you have any questions, any problems that you're experiencing with the 3D printer, let me know. We can talk it through, see what I can do. But if you have any questions for the assignment that's due tonight, stick around. I can answer some of those questions. But that's pretty much what I have. I also, oh yeah, and one last thing, I also uploaded a lot of other assignments as well, if you needed those. If you get ahead, or if this thing is just sitting there 3D printing and you want to work on the next assignment, it's up there as well. So, but all right, great. Thanks everyone. And if you got any questions for the assignment, just stick around. Cool.
Cool. Thanks.
Yeah, no problem.
Thank you.
John, I do have a question about the assignment. So I think I have most of it figured out, but